Hey, welcome. You ever wonder how your GPS knows exactly how fast you're going and in what direction? Or, how a video game figures out a character's jump? Well, it all comes down to this one really powerful concept in physics, vectors. Seriously, learning how to handle these is a total game changer, because it's the only way to solve problems where you've got forces pulling in all sorts of different directions. And today, we're going to master that core skill. All right, let's dive in and start breaking things down. So, to get us going, picture this. A superhero is just blasting through the sky. We know their speedometer says 100 meters per second. But look, they're not going straight across, and they're not going straight down. They're flying at an angle. So the real question is, how do we talk about that diagonal motion in simple, straight-line terms? How much of that is forward, and how much is down?
And the answer to that question is something called vector components. You can just think of them as the basic building blocks of any angled movement. Instead of trying to deal with one tricky diagonal line, we just break it down into two way simpler paths, one that's purely horizontal and one that's purely vertical. Easy.
And right here, this is the main idea for today. We can take any diagonal vector, it doesn't matter what angle it's at, and describe it perfectly using just two simple parts, better at right angles to each other. We call the side-to-side part the x component and the up and down part the y component. And together, those two little pieces tell the vector's whole story.
Okay, so let's get back to our superhero problem and tackle it head on. We're going to start with the complete vector, that's the 100 meters per second at an angle, and see exactly how to break it down into those simple x and y parts.
So what do we know? We know the long side of our triangle, the hypotenuse. That's our hero's total speed, 100 meters per second. And we know the angle, 30 degrees south of east. That little detail is going to be super important. So if we just sketch this out on an XY grid, you can already see the right-angled triangle we're about to solve.
All right, here's where we connect a little geometry to our problem. To find that horizontal part, which we'll call Vx, we just need to look at its relationship to that 30-degree angle. See how it's right next to it? It's the adjacent side. And trigonometry tells us that for the adjacent side, we use cosine. You probably remember SOHCAHTOA from math class? Well, cosine is adjacent over hypotenuse. That's exactly what we need right now.
And the calculation itself is pretty simple. We just take the total velocity, 100, and we multiply it by the cosine of 30 degrees. Pop that in a calculator, and you get 86 meters per second. So there it is. That's the forward speed, the pure eastward part of the hero's motion.
Now for the other piece of the puzzle, the vertical component, let's call it V. If you look at our triangle, that's the side that's opposite our 30-degree angle. And for the opposite side, we always use the sine function. You see the pattern, right? Adjacent gets cosine, opposite gets sine. Just like before, we plug in our numbers, 100 meters per second times the sine of 30 degrees, and that gives us 50 meters per second. So great, we've got our answers, 86 meters per second forward and 50 meters per second down. Or do we?
Before we call it a day, we have to ask a really important question. The math gave us a positive number, 50. But think about it. Which way is our hero actually flying? Are they moving up or are they moving down?
And this right here is a crucial rule for vectors. The problem said the hero was flying south of east. On a normal graph, south or down is in the negative y direction. So our y component isn't just 50, it's actually negative 50. That little minus sign is what tells us the direction. It's the whole story.
Now there's a really easy way to remember this using quadrants. Since our hero is flying into that bottom right section of the graph, what we call quadrant 4, the x value is positive, but the y value has to be negative. This is a fantastic little mental check to make sure your signs are always correct. So check this out. There are actually two great ways to get this right every single time. Method A is what we just did. You use the simple angle, like 30 degrees, and then you use your brain to add the plus or minus sign based on the quadrant. Or you can use method B. Measure the full angle all the way around from the start, which is 330 degrees in this case. Your calculator is smart enough to know that angle lands in quadrant 4, and it will give you that negative sign automatically. Both methods get you to the exact same correct answer.
Okay, so we just successfully took a vector and broke it down into its basic parts. Pretty cool. Now, let's flip the script. What if you start with the parts and you want to build the whole vector? Let's take a look at a brand new problem.
So imagine an airplane. We know its forward speed, the x component, is 120 meters per second to the east, and we know its sideways push, the y component, is 80 meters per second to the north. But those are just the parts. The real question is, what's its actual total speed through the air?
To put these two pieces back together, we turn to an old friend, the Pythagorean theorem. It's that simple. The horizontal and vertical parts form the two sides of a right-angled triangle, and the total velocity we're looking for, well, that's just the hypotenuse.
And the process couldn't be easier. It's just 3 steps. First, you square each of the component speeds. Then, you add those two numbers together. And finally, you just take the square root of that sum to find the length of the hypotenuse.
And there it is. The plane isn't traveling at 120, and it's not traveling at 80. Its true total speed through the air is a much faster 144.2 meters per second. That number is the magnitude of its velocity vector. But hold on, finding the speed is only half the battle. Remember, a vector isn't just a number, it has both magnitude and direction. So we know how fast the plane is going, but now we need to know exactly which way it's pointing. We got to find that angle. Now this part is brilliant. Because we know all 3 sides of our triangle, the 2 components we started with, and the hypotenuse we just found, we can use any of the inverse trig functions to find the angle. You can use inverse tangent, inverse cosine, or inverse sine. Look at that. They all give us the exact same answer, 33 degrees. It's foolproof.
So let's just do a quick recap of the powerful new toolkit you've just built. First, you now know how to deconstruct a vector into its x and y parts using sine and cosine. Second, you know the crucial importance of minding the signs to get the direction right. Third, you know how to reconstruct a full vector from its parts using Pythagoras. And finally, you can pinpoint the exact angle using inverse trig. You've got all the tools.
Really, when you boil it all down, that's the complete story of vector components. It's this beautiful skill of taking something complex, breaking it into simple parts, and then being able to build it right back up again.
So for our airplane, we have the complete picture. It's traveling at 144.2 meters per second at an angle of 33 degrees north of east. That is the full, complete answer.
And with that, you now have the fundamental skills to analyze basically any motion in 2 dimensions. I mean, whether it's the force of the wind on a skyscraper, the path of a soccer ball after it's kicked, or the trajectory of a rocket. So the only question left is, what are you going to analyze first?